Hey everyone, welcome back to the channel. In this video, we're building a smart IoT energy meter that doesn't just monitor readings, it protects your home appliances from overvoltage, undervoltage, and overcurrent automatically. We'll be using an ESP8266, a PZEM-004T energy sensor, and a 20x4 LCD to display live readings, plus an interactive web dashboard where you can control everything in real time from your smartphone. By the end of this video, you'll see how this project can sense, display, and protect your electrical setup like a pro. So grab your tools and let's get started. If you want to build your own custom project like this one, or need modifications, something unique at affordable costs, make sure to check out the page linked in the description below. Also, you can reach me directly through this mail address info@circuitdiagrams.in. Just drop your idea, and I'll help you bring it to life. ESP8266 NodeMCU. It connects your system to the Wi-Fi and sends all the data to the web dashboard. It's a DC to DC buck converter, which means it takes a higher voltage input, like 12 volts or even 24 volts, and steps it down to a stable 3.3 volts output. We'll use this module to power our NodeMCU safely. PZEM-004T. This is the heart of the measurement system. It accurately measures voltage, current, power, and energy consumption in real time. It communicates with the ESP8266 through serial communication, giving us live data straight from the AC mains. 20x4 LCD display. This display gives your project that real professional look. It can show up to 4 lines of data with 20 characters per line, so you can easily display voltage, current, power, and even energy usage all at once. Now this tiny module here, the I2C interface board. It connects to the back of our 20x4 LCD display and makes wiring super simple. Instead of connecting 16 pins, you only need 4 wires: VCC, GND, SDA, and SCL. Here's the protector of your system, the 5-volt relay module. We'll use it to automatically disconnect the load when voltage or current goes beyond safe limits. That means overvoltage, undervoltage, or overcurrent situations. Next, we've got this push button, small but mighty. We'll use it to change the display page to see all types of readings. The male and female header pins are the secret to neat, reliable connections. They help you plug and unplug your components easily, especially if you're using modules like the NodeMCU or the LCD. And finally, the Vero board, also called perf board. Once you've tested your circuit on a breadboard, you can solder everything onto this to make your project permanent and sturdy. Alright guys, check this out. Here it is, the fully mounted IoT smart energy meter built neatly on a double-sided Vero board. Everything you see here has been carefully placed, soldered, and connected, and it's looking super clean and professional. Now let's take a look at the LCD display connections. This is our 20x4 LCD module with an I2C interface attached at the back. The I2C module makes the wiring super simple. Instead of connecting 16 different pins, we only need 4 wires to hook it up to the NodeMCU. The VCC pin from the I2C board goes to the 5-volt input pin from the buck converter module, since this LCD can handle it easily. The GND pin connects straight to the GND of the buck converter. The SDA line connects to D2 on the NodeMCU, and the SCL line goes to D1. This setup keeps the wiring super clean and makes the display update in real time with our voltage, current, and power readings. Now let's connect our current transformer coil, or CT sensor, to the PZEM-004T energy monitoring module. Simply take the 2 wires coming from the CT coil and connect them here. 1 wire to each CT terminal. This CT coil is what measures the current flowing through the load, and it connects directly to the 2 small screw terminals labeled CT on the PZEM board. It doesn't matter which way around you connect them. The CT coil works both ways for AC measurement. And that's it. Your current measurement setup is done, safe, isolated, and ready to send accurate current readings to the NodeMCU. Now, when current flows through the load wire that passes through the CT coil's ring, it induces a tiny magnetic current that the PZEM reads accurately. Just make sure the load wire passes through the center of the CT coil, and only 1 wire, not both live and neutral, goes through the ring. So, while testing the circuit, I ran into a small issue. My mechanical relay module started acting up. It was sometimes chattering or not switching properly. Instead of replacing it with another regular relay, I decided to go one step better and switch to a solid-state relay. Alright guys, now let's look at how we connect the voltage sensing terminals of our PZEM-004T module to the AC main supply. Here we are using red wire for the phase live connection and blue wire for the neutral. These two connections allow the PZEM to continuously monitor the mains voltage and measure power and energy consumption accurately. Now insert both wires to the AC main socket safely. This is where we connect our red phase wire through to the relay common terminal and connect it to the AC phase point by passing through the CT coil. Make sure only the phase wire, not the neutral, passes through the CT coil's ring. When the relay is activated, the phase line connects internally and allows current to flow to the load. If the system detects overvoltage, undervoltage, or overcurrent, the relay switches off, cutting the phase line, instantly isolating the load for protection. Now take the red phase wire coming from the load socket and connect it to the NO terminal on the relay module. Remember, NO stands for normally open, which means that when the relay is off, this terminal is disconnected. No power flows to the load. Now for the final step, take the blue neutral wires from the load socket and insert directly on the AC mains neutral point. For this project, we're using a simple 5-volt DC jack to power the whole circuit. This 5-volt line will feed our NodeMCU 3.3 volt through the CA1235 step-down module, and also feed 5-volt supply to the relay module, PZEM-004T, and LCD display. We've got everything wired up, the components are mounted neatly, and now it's time to power up the system and see our IoT smart energy meter in action. Alright guys, check this out. When we power up, the LCD first displays our project title, giving it that professional startup look. Then once the NodeMCU connects to Wi-Fi, it instantly shows the IP address right below. That's how we can access the live IoT dashboard from any device. After connection, the main screen pops up showing voltage, current, power, and system status. And when I press this push button, the display switches to the second page, now showing energy, power factor, frequency, and the current mode. Also, all protection thresholds present value. Super smooth, super smart. Exactly how a modern IoT energy meter should look. When no AC power is detected, all the values show 0 at first. After switch on the power, voltage shows around 232 volts and status is in manual mode. When the system starts for the first time, it's in manual mode and the relay stays off by default. That's done on purpose to prevent any sudden damage from overvoltage, undervoltage, or overcurrent at startup. Once you've checked that all the protection features are working properly, you can easily switch the system to auto mode from the web dashboard, and then the relay will start operating automatically based on live conditions. Alright guys, time to test the setup using this 5-watt LED bulb. I've connected it as our AC load. Now I'll switch on the power for both voltage sensing and current sensing. Now let's check out the mobile web dashboard. As you can see, it's showing live readings of voltage, current, power, and energy, all streaming directly from our smart meter in real time. Everything updates instantly. No lag, no delay, just smooth IoT monitoring right at your fingertips. And here you can set all the protection limits remotely. And here's the best part. I'm going to tap this Auto Protection Mode button. Boom! The system switches from manual to auto, and now the relay and protection features are fully automated. You can see the relay click on, and the bulb instantly glow up. On the main screen, we've got voltage approximately 233 volts, current 0.03 amps, power 4.5 watts, and status is set to auto. Sweet and steady. Now I am pressing the button. Page 2 pops up showing energy 0.034 kilowatt hours, power factor 0.67, and frequency 50 Hz, which is Indian standards. And here's something cool. In manual mode, we can control the load directly from the dashboard. When I tap the turn off button, the relay clicks and the bulb turn off instantly. Tap it again, and it turns on back immediately. Alright guys, now it's time to test the protection features of our smart IoT energy meter. This is where the real magic happens. You can see at present overvoltage is set to 260 volts. But as I have no variable transformer to test it out, I will set the value below the present voltage value from the dashboard. I'll simply lower this threshold from the dashboard to below our present voltage level, around 229 volts. Once I save the setting, the system instantly detects the voltage as over the new limit, and the relay trips off automatically, showing that our overvoltage protection is working perfectly. Now it's time to test the undervoltage protection feature. Right now, the undervoltage limit is set to 180 volts, which is way below our current mains voltage of about 231 volts. Since I can't drop the voltage physically, I'll just increase the undervoltage limit from the dashboard to a value above the present mains, say around 232 volts. The moment I save that setting, the system detects the voltage as below the new threshold and the relay instantly turns off, proving our undervoltage protection is working perfectly. Alright guys, now it's time to test the overcurrent protection feature. At the moment, the overcurrent limit is set to 30 amps, which is way higher than our small 5-watt test load, so the system stays on normally. To simulate an overcurrent trip, I'll simply reduce the limit from the dashboard to a much lower value, which is 0.02 ampere, below our actual current reading, which is 0.03 ampere. You can see here, as soon as the system detects overcurrent, the relay immediately turns off, and the system automatically switches to manual off mode. This isn't a bug, it's actually a safety feature. When an overcurrent happens, instead of rapidly turning the relay on and off, which could seriously damage your appliances or wiring, the system locks itself in manual mode. That means you'll need to manually enable auto protection again from the dashboard once the issue is fixed or overcurrent still exists. They'd automatically turn off the power and switch to manual off again. Now it's time to test our system with a big load, and for that, I'm using a heat gun. Let's power it up, and there it goes. You can see the LCD and dashboard instantly show a spike in current and power readings, everything updating live in real time. The voltage stays stable, current increases as expected, and the system handles the load perfectly. This test really proves how reliable our smart IoT energy meter is, even under high power conditions. So whether it's a light bulb or a heavy appliance, this system can monitor, protect, and control your load safely and smartly. And finally, here's one last cool feature, the power status indicator. When the AC power is on, a green animated circle splashing, showing that the power is flowing safely to the load. And as soon as the power off, it switches to a red glowing circle, indicating that power is disconnected. It's a small touch, but it makes the whole system feel smart, modern, and interactive. And that wraps up our Smart IoT Energy Meter project. We've got real-time monitoring, full protection, web control, and a clean display interface, all powered by the ESP8266 and PZEM-004T. If you enjoyed this project, don't forget to like, share, and subscribe for more awesome IoT and electronics projects. Thanks for watching, and I'll see you in the next one.